So when you're evaluating this integral, remember y is the variable, okay? And 9 minus x squared, these are all constants, right? So if this is a constant, what is it going to be? It's antiderivative. Think about if you have this question, guys.
9 minus x.
9 minus x squared. This is a constant, and then
Sorry, yes or no?
should we multiply by a y in the end?
Yes.
Okay. It's kind of like this. If you see integral of 2 dy, right? Then you know antiderivative is going to be 2y. Folks, do you see that?
Yes.
Okay, so here 9 minus x squared is a constant, therefore its antiderivative will be 9 minus x squared times y. Okay, and then let's evaluate the y goes from 0 to 1. Y starts at 0, ends at 1, right? And over next will just be simply plug 1 in and plug 0 in, and then do the subtraction of those two results. So first of all, let's plug 1 in for y. So we have 9 minus x squared times 1, and subtract 9 minus x squared times 0, right? Therefore, will be 9 minus x squared. Okay, that is for the inner integral, the first layer. Okay, first layer. Let me see if I can swap my color. Okay, so next. So you finish this integral, which is the inside. Next, we're gonna go the outside. Okay, so outside will be integral -2 to 2. And to the rightmost, we have dx. And currently, for this boxed inner part, that's what we just computed as 9 minus x squared. So this whole thing right here is 9 minus x squared. So I'm going to write this as 9 minus x squared based on what we computed. Is that good so far?
Yes.
Okay. Now this is just a regular integration that we are familiar with, right?
Mm-hmm.
Variable is x and you're integrating with respect to x. So antiderivative, you can do antiderivative of 9, which will be 9x. Antiderivative of x squared, that's going to be x cubed over 3. And then we're going to evaluate at x equals -2 and positive 2. Right? And we should plug 2 in first. Right? 2 goes in first. We have 9 times 2 minus 2 cubed over 3. Is that good so far?
Yes.
And then we're going to plug -2 in for x. We have 9 times -2 minus -2 cubed over 3, right?
Mm-hmm.
And over next is just the evaluation of this number, okay? I can distribute this negative sign to everything inside, and let's see what do we have. First of all, we have 18 minus 8 over 3, and this minus turns to plus 18, and the minus turns to plus again. These two negative signs turns to plus, and then you still have a -2 cubed, which is -8, right? -8 over 3. Is that good so far?
Yes.
Right track? Okay. So we can combine the integers with the integers. We have 18 plus 18, that's 36. And -8 over 3 minus minus 8 over 3, that subtracts 16 over 3, right?
Mm-hmm.
And eventually you can combine this into one single fraction. So 3 in the bottom, 36 times 3, that's 1/8 minus 16. There we have 92 over 3. That's going to be this double integral. Okay. So let's kind of like recall what we just did for this for this double integral. First of all, we recognize the inside of the layer. Okay, that's the inner integral, and then we have the outer integral. You start with the inside and you go to the outside. The inside is integral of 0 to 1, 9 minus x squared dy. Here, y is the variable, therefore 9 minus x squared is treated as a constant. You can always recall this. You can use some simple examples to see what's going to be the possible antiderivative. If you look at the case, integral of 2 dy, antiderivative is going to be 2y. So similarly here, 9 minus x squared is treated as a constant. Antiderivative will be 9 minus x squared times y. And then just evaluate at the two endpoints. You will get 9 minus x squared. And that would be able to replace this inner integral, okay, the box. The box is 9 minus x squared. And then you just go ahead and work on the outside layer, integral -2 to 2 dx as the outside setup. The part in the middle could be replaced by what we just computed, 9 minus x squared. And the rest of the work is just similar to what we did in calculus 1, right?
Yeah.
So the only thing that has been added over here is you have an inner layer that should take care of first. And in this inner layer, you may have two variables which you will need to determine which is the variable you are integrating with respect to. Okay. All right, let's look at more examples. Next, we have integral from 0 to 1, integral from 0 to 1, x e to the xy dy dx. So let's use the same idea as we just did. Let's start with the inside. And then go to the outside. Okay. First of all, we have integral from 0 to 1, x e to the xy dy. Okay, now let's think about it. Here, y is the variable, right? Y is the variable. So x would be considered as a constant, okay, constant scalar, just constant coefficient, right?
Mm-hmm.
If you, I'm sorry, did you say anything, Jaquan?
Could we pull the x out of the integration?
Absolutely, because x is just a constant coefficient. So if you want to, you can feel free to pull the x to the front. The x could be pulled to the front, and 0 to 1, e raised to x to the y, e raised to x, y, dy, right?
Mm-hmm.
Okay, now you should consider what is the antiderivative. Again, y is the variable, so you can always use some simple example to help you to find the antiderivative you can consider. And first of all, you may not be very familiar, so you can consider some easy cases. Integral of e raised to the, say, some number 2, and with variable y, dy, right?
Mm-hmm.
Because these cases we're familiar with. What's the antiderivative of this? E to the 2y.
Is it e to the 2y over 2?
Correct. So e to the 2y, and then we should divide by 2 because 2 would be as a from the chain rule. When you take the derivative, you have additional 2, right? So we should divide by that 2. Make sense?
Mm-hmm.
Okay. So same thing we can apply to here. Let's first of all copy the x as it is. And for e to the xy, first of all, be e to the xy. And then we should divide by the derivative of xy from the chain rule, right, with respect to y, which is going to be x. And here, y goes from 0 to 1. Okay, therefore x and x would be reduced. In general, the antiderivative in this case will just be e to the xy. And our y should go from 0 to 1, right?
Mm-hmm.
Okay. Now, right before we go evaluation, let's think about what this antiderivative makes sense. E to the xy. If you take derivative with respect to y, do we have this integrand?
Yes.
Yeah, we would have e to the xy first of all, right? And then we should do chain rule with respect to y. That will give you additional x. So this is a correct antiderivative, okay? And then let's plug 1 in and plug 0 in. So we should have e raised to the x times 1, which is x, minus e raised to the x times 0, which is 0. Here, because we're doing e to the 0, you can't say this is 0. This is actually a value, which is 1. So it'd be e to the x minus 1. Good?
Mm-hmm.
Okay, so this inner box just matches e to the x minus 1, right?
Yep.
And then we should just go and go to the outer box. Okay, so next you should go to the outer box here. So second, let's do integrals from 0 to 1 dx, 0 to 1 dx, and put whichever we have obtained from an inner box, which is e to the x minus 1 here. Okay, this is a pretty easy case, right? Back into calculus 2. Antiderivative of e to the x will be e to the x. Negative 1, antiderivative will be minus x. You guys okay?
Mm-hmm.
And our x goes from 0 to 1 again. Let's evaluate. First of all, x equals 1. So we should have e to the first minus 1. Next, let's evaluate when x equals 0. So we have e to the 0s minus 0. Which eventually would come up with e minus 1 and minus another 1, right? Guys, you have e to the 0 here, so that's another 1. So we get e minus 2 as the final answer. Good so far?
Yes.
Okay. So in this case, we looked at the inner box, and we noticed that when y is treated as the variable, x as just a constant coefficient. This one, x could be pulled out, okay? And then you can just focus on e to the xy, find its antiderivative with respect to y. So you need to divide by x, and then do the evaluation. Is everything good for this example 2?
Yes.
Okay, now let's move on to example 3. We're getting a little bit more complicated this time. Okay. So example 3, we have integral from 0 to 1, 0 to 1, y over xy plus 1 squared dx dy. Okay. Same thing here. You should start with your inner integral 0 to 1, y over xy plus 1 square dx. And again, if you would like to pull out y, feel free to do so, because x is the variable, right? So it's y integral 0 to 1, 1 over xy plus 1 squared dx. Okay, let's think about what's the antiderivative. of this?
It's you could make the denominator -2.
Okay, we can rewrite it. Yes, let's rewrite this in terms of negative exponent. So it'll be y integral 0 to 1. And let's rewrite this as xy plus 1 raised to the -2 dx, right?
Mm-hmm.
Okay, pay attention to variable x is your variable. Okay. So the antiderivative. Okay, you can again recall the case in calculus 1. What if you have, say, 2x plus 1 raised to the -2 dx, right?
Mm-hmm.
We're going to do 2x plus 1 raised to -1 over -1. First of all, the power rule. And then due to the chain rule, you're going to have additional 2 coming up, right? Additional 2. So we're going to divide by that 2. Right?
Mm-hmm.
So same thing here. First of all, let's use the power rule. We're going to have xy plus 1 raised to the -1 divided by -1. And by the chain rule, okay, by the chain rule, this xy plus 1 itself is going to have additional derivative, which is
y,
which is a constant right over here. So you're going to divide by that y. Okay, good. So here x goes from 0 to 1, right?
Mm-hmm.
The y would be reduced again here. If you want to write it in a better way for you to see it more directly, you can say this is negative, right? Negative reciprocal, right? Is that reciprocal of xy plus 1? And my x goes from 0 to 1. Okay, once you have the antiderivative, the next step is pretty straightforward. So you're going to plug 1 in for the x and plug 0 in for the x, right?
Mm-hmm.
Once we plug 1 in, we have a -1 over y plus 1. Okay, next let's plug 0 in. Once you plug 0 in, this part will just be 0. We have -1 as a result. So it's minus -1. Okay, so this could be simplified as minus minus +1 minus 1 over +1. Good so far?
Mm-hmm.
For the inner integral. Okay, next let's go back to the red color for the outer side. So next you're gonna go 0 to 1 dy. 0 to 1 dy. I'm gonna replace the box by 1 minus 1 over y plus 1. Okay, I think this integral is pretty straightforward, right? Okay, guys, what's going to be the antiderivative?
Y minus log of
Y minus natural log of y plus 1. Good. 1 will just match y, and reciprocal function will just match natural log function, right, for antiderivative. All right, so y starts at 0 and ends at 1. Okay. And next again, plug in 1 for the y and plug 0 for the y. Okay, when we plug in 1, we have 1 minus ln 2, natural log 2. When we plug 0, we have 0 minus natural log 0 plus 1, which is 1. And don't forget, what's the value of natural log 1, guys?
0.
Yeah, so this is just, again, another 0, right? This is the same as 0. So eventually the answer will just be 1 minus natural log 2. All right?
Mm-hmm.
Okay, so we've done 3 examples, and all of these kind of use the same strategy. Iterated integral, so you go from the inside to the outside. Okay, that's how you would evaluate these double integrals. Oh, so next example, let's look at the application. Let's find the volume of the solid under the surface of this given function over the specified region. This is a specified region. Okay. If we sketch this region, okay, you can tell that x is between 0 and 2, y is between 0 and 3. So this region R is rectangular, right?
Mm-hmm.
Rectangular. If it's rectangular, then differential of area would just be dx dy or dy dx. It's up to you, whichever you want to go. Okay, either way would be fine.
Mm-hmm.
So the volume will just be double integral of the function function times differential of area over region R, right?
Mm-hmm.
Okay, so we can go. Function will be 25 minus x squared minus y squared. dA, the dA could be dx dy, could be dy dx. Just let's see, if we go dx dy, then x would match this integral. Therefore, the value would start at 0, ends at 2. So we're going to put 0, 2 there. Okay? So don't swap those, don't randomly interchange the numbers for the integral.
Mm-hmm.
So for y, so dy should match the outer layer. The value would be from 0 to 3, right? Oopsie, 0 to 3. Okay. Of course, if you want to go dy dx, feel free to do so. If you want to do 25 minus x squared minus y squared, dy dx, that's going to be the same volume. And this time we're going to write y would be 0 to 3, and x would be 0 to 2. Okay?
Mm-hmm.
All right, I'll give you guys a few minutes to evaluate either one of those, and let's see what's going to be the volume here. Okay? Okay, did you guys go dx dy or dy dx?
I did dx dy.
Okay, dx dy. That's fine, because in this case, in this question, it doesn't matter. Okay, you should have exactly the same answer towards the end. Let me choose another color here real quick. All right. The integrand is pretty straightforward. It's just the evaluation might be a little bit tedious. Okay. Over here, so integral 0 to 2, 25 minus x squared minus y squared dx. What's the antiderivative here?
25y minus yx squared minus y cubed divided by 3.
Okay, Romero, here, what's the variable? Be careful.
Oh, never mind.
Here, x is the variable, right? So
No, I think I did the other one then.
did you do? Yeah, you probably did the other one.
Yeah, I did the other one, yeah.
You can switch to the other one. So if x is the variable, antiderivative will be 25x minus, which this will just be x cubed over 3. And for the y squared, it's a constant, therefore antiderivative will be y squared x. Right?
Mm-hmm.
All right, and then x goes from 0 to 2. So let's see. If you do 0 to 2, I'm going to plug 2 in for x. Make sure you are simply plug them into the right variable. Okay, so 25 times 2, that's 50. And you have 2 cubed over 3, which is 8 over 3, minus y squared times the 2. So that's 2y squared. That's what you get when you plug 2 in. If you plug 0 in, I have 0, 0, and 0, right? So the second part will just be 0. So the first part, I have 50 minus 8 over 3 minus 2y squared. I can combine these two, 50 minus 8 over 3. So 3 will be the common denominator. I have 150 minus 8. So it'll be 142 and minus 2y squared. So that's going to be the inner layer, right? And then we can go ahead and choose the outer layer. Go ahead for the outer layer. Next will be 0 to 3 dy. And I'm going to put this in. 142 over 3 minus 2y squared. And you guys probably haven't noticed, once you go to the outer layer, the variable would match the variable that appeared in your integrand, right? There's no other variables over here. So it just comes down to the regular integration. Antiderivative is pretty straightforward, 142 over 3 y, because that's a constant. The antiderivative will be 142 over 3 y, minus 2 times antiderivative of y squared, which would be y cubed over 3, and you plug 0 and 3 in, right? If you plug 3 in, I have 142 over 3 times 3, which 3 would be reduced, minus 2 times 3 in, so 27 over 3. Once you plug 0 in, I have 0 here and 0 there, so it won't affect my result. So eventually, I get actually whole numbers, because 3 and 3 reduced, you get 142. And the 3 and 27 reduced to be 9, so 2 times 9, which is 18. So you should have 124 as your final result. Is that what you guys got?
I got 114. I probably did something incorrectly.
Yeah, probably something messed up for the calculation. But even if you did dy dx, you should have 124 towards the end as well. Okay?
Yeah.
All right. So it's easy to set up in this question, right? Setting up is not difficult because of the rectangular region R that we have. I'm going to show you the graph that kind of like matches what this problem talks about. So z equals 25 minus x squared minus y squared. It's easy for the plot. Its graph is going to be like an upside down paraboloid. Okay. And my x is from 0 to 2, which is small area over here, and 0 to 3, which is small area there. So you can tell if this is the region R, you're going to have a corresponding solid, right? Matches this part of the graph. So that volume is going to be 124 as we have computed over here. Okay. All right.
Mm-hmm.
All right, so that's example 4. Next, I want to introduce a very useful conclusion. Okay, useful conclusion. This is called iterated integral for separable function. Okay, separable function. For those of you who's in my differential equation classes, oh, you guys had calculus 2, right? In calculus 2, differential equation was a part of it. Probably recognize the name separable function. Okay. What kind of function is called separable function? So those functions are function of two variable f of x, y that could be written as a product of function x only and function y only. So if my function f of x, y is a function of x times a function of y, then this function f of x, y is called a separable function. Okay. Let me highlight this piece over here. Okay. A separable function. For a separable function, it's easy to conduct the double integral calculation. You can go from double integral to simple integral. And notice that from double integral, I have converted that to the multiplication of two single integrals, right?
Mm-hmm.
And one is only about x and one is only about y. And you may ask, why can we do this? Let's do a quick proof of this conclusion over here. Okay. So quick proof. Let's do the left-hand side of my identity I'm proving. So a, b, c, d, function f of x, y, dy, dx. And here, function f of x, y is separable. If this is separable, we know then this function f of x, y could be written as a function of x, which is gx, and a function of y, which is h of y only. Right. Good so far?
Mm-hmm.
Okay. So it turns to this double integral form, right? Okay, then we can just follow whatever we have done before. We can go from the inner integral and then work on to the outer integral. So here, inner integral c to d, gx, h of y, dy. Now notice that y is the variable. So g of x will just be a constant coefficient. So same thing again, we can pull this constant coefficient to the front. That will be g of x, integral c to d, h of y, dy. Is that good?
Mm-hmm.
Okay. And we don't know what's hy here, right? So we can just leave this integral as it is. So that part would match this box. Okay. Okay, next we're gonna go outer integral. So we have a to b dx, and we have g of x, c to d, h of y, dy. And keep in mind, okay, when you are doing this part, integral c to d, h of y, dy, what we're doing is we're finding antiderivative of this h of y, and then evaluate d and c for the y's, right?
Mm-hmm.
So for this part, it no longer has any y's. All the y's has been replaced by d and c. So this is going to be actually a number, right?
Mm-hmm.
Think about it. You find an antiderivative, and you're going to simply substitute all the y's by the constant c and d. So this is a number, which means here you have a number that's a constant coefficient, which again you can pull outside of this integral. So that turns out to be integral c to d, h of y, dy. I'm pulling it completely to the front. And what's left inside will just be integral a to b, g of x, dx. Okay?
Mm-hmm.
Have we finished our proof?
No.
Almost there. But is
Almost.
that the same as our proof? So in the right-hand side, we have a multiplication of two integrals, right? Two integrals. One is integral with respect to y, and one is integral with respect to x. So that's going to be the same as what you see here. Integral with respect to x and integral with respect to y. Okay. So that you can say that just equals to the right-hand side. Okay?
Mm-hmm.
Okay, so this works for separable function. I do want to put a note here. Okay, you can't always use this for all kinds of separable function. The note, let's see, what do I want to do? I'm going to change to another color. So the note would be, okay. For this conclusion, first note is you can use this for separable function, of course. Secondly, when you use this, you gotta make sure this is over rectangular region. Okay, so all the limits are constant limits, a to b, c to d. This is a note to when you can use this conclusion. Is that good so far?
Yes.
Okay, so the good thing is you can see that in this case, the double integral just turns into the multiplication of two single integrals. Okay. So the example 5, evaluate this iterated integral. This is the integrand, and here is the limits for integration. Okay. Let's think about, it looks like a little bit complicated if you look at the integrand over here, but if you look at the integrand here, f of xy, which is xy e to the x squared over 1 plus y squared, is this separable?
Yes.
Okay. It is actually, could be separated as a function of x only. So we x e to the x squared, and a function of y only, so y over 1 plus y squared, right?
Mm-hmm.
This is indeed separable. Okay. Secondly, is this over a rectangular region?
Yes.
Yeah, you gotta just simply check if the limits are all constants. Okay. So over here, the limits are on, let's see. Okay, where's my, okay. This is over rectangular region. Good. So with these two conclusions, with these two conditions being met, we can use that conclusion. Okay. So therefore, let's just say this double integral could be simplified into single integral. Okay. One is about dy, one is about dx. It doesn't matter which one you go first. Okay. So I can put all the y's together. So y over 1 plus y squared. Put x all together, x e to the x squared. Let's check their limits. What's the boundary of x? What is the interval for y? What should I put?
Boundary for y is 0 and 1.
Yeah, so y would be goes from 0 to 1. Boundary of x, here the interval of x will be from 0 to square root of natural log 2, right?
Mm-hmm.
So you see, I can just put them in this way. It's pretty straightforward and goes back to calculus 2 and calculus 2 and calculus 1, right? Oh, no, calculus 2 as well, sorry. Here, y over 1 plus y squared, do you guys recognize its antiderivative?
Mm.
Would it be the natural log of 1 plus y squared over 2?
Good, yes, because this y comes from the derivative of 1 plus y squared. So this is a reciprocal of 1 plus y squared, right? So reciprocal function will be natural log of 1 plus y squared. And think about it, it's going to have a like additional derivative, which is 2y. So we're going to divide by 2. So ln 1 plus y squared over 2. Y goes from 0 to 1. Very good. Second part, x e raised to the x squared. What's going to be this antiderivative?
E to the x squared over 2?
Yes, e to the x squared over 2. You can just think of, I can complete this by using substitution method, right? If I let x squared to be u substitution, you'll be able to do this question. The antiderivative will be e to the x squared and divide by 2. Again, the 2 comes from the chain rule. Here, x goes from 0 to root of natural log 2. So I just need to multiply these two. Okay. All right, the first thing, let's plug 1 in and plug 0 in. I should have natural log 1 plus 1, which is 2, over 2, minus, plug 0 in, natural log 1 over 2. Subtract the second part, plug root of natural log 2 in, so I should have e raised to the root of natural log 2, it's squared, which is natural log 2 over 2. Oh, sorry, this should be multiply, right? Multiply. Carry down this multiple sign. And minus, when you plug 0 in, so e to the zeros over 2. Good so far?
Mm-hmm.
Yeah, let's see what do we have in the end. So we understand natural log 1, which is 0, right? This part is just 0. So I have natural log 2 over 2 times the second part. I have e raised to natural log 2. What is that?
The entire thing is just equal to 1.
Yeah. Yeah, so e and the natural log will be kind of canceled out, right? E and natural log cancel out. So you get 2 over 2, which is 1, minus, this is 1 over 2, 1 half. So I have natural log 2 over 2 times additional 1 half. So this will be natural log 2 over 4. Is everything good?
Yes.
Okay. So this is one example that we can use the conclusion that we have talked about for separable. Separable function and over rectangular region. So we can break that down into 2 single integrals and just evaluate each and then multiply them towards the end. Okay. It's pretty convenient for separable functions. All right, over next, we want to talk about iterated integrals when the limits are not constants, which means they are not rectangular region. Okay, they're not rectangular region. The ones we have seen before, like these ones, okay, x is between 2 constant, y is between 2 constant, the region tends to be, the region would be definitely rectangular. But if you have non-constant, then you would have a non-rectangular region. This would be mostly talk about it in the next section, but I would just want to introduce the way that we solve it, we evaluate it. Okay, like example 6. Okay, example 6 is related to example 7, but let's first start with these kind of integral. Suppose I'm doing integral 1 to x 2xy plus 3y squared dy. What's going to be its antiderivative? Y is the variable. Okay, so I should have 2x as it is, and to derive y will be y squared over 2 plus 3 times
Y cubed divided by 3.
y cubed over 3. Yeah, and this time you see y is not bounded by 2 constants. It's bounded by 1 and x. So y will be 1 to x. But you just treat this x as a constant, as you just do the regular way as we do, okay? So 2 and a 2 would be reduced. I get xy squared plus y cubed. Y goes from 1 to x. Now, the only thing different here is instead of plugging a constant for y, this time we'll be plug x in for y. So x in for y, x in for y, first of all. So you should have x times x squared plus x cubed, and then plug 1 in for y. X times 1 squared plus 1 cubed. Everything good?
Yes.
The only thing you see different is you're going to plug in a non-constant, right? So we have x cubed plus x cubed, but the same way for computation. So 2x cubed minus, this is x plus 1. So I can say minus x and minus 1. Good? All right. I'll attach the answer here. You have 2x cubed minus x minus 1. Okay, so this integral is actually related to the next double integral. Okay, see this double integral is integral from 1 to 2, 1 to x, 2xy plus 3y squared dy dx. We actually have already done the inner integral. Okay, so first we already got 1 to x, 2xy plus 3y squared dy is that x cubed minus x, 2x cubed minus x minus 1. That's 2x cubed minus x minus 1. So we have already completed this inner integral by example 6. Okay, so second, let's just take care of the outer layer. So 1 to 2 dx, 2x cubed minus x minus 1. So same thing, right? Finding antiderivative, you have 2x to the 4th over 4 minus x squared over 2 and minus x. And x goes from 1 to 2. So 2 and 4 can be reduced to be x to the 4th over 2 and minus x squared over 2 minus x. Plug 2 in everywhere for x. We got 16 over 2 minus 4 over 2 minus 2. And then plug 1 in. 1/2 minus 1/2 minus 1. Okay, easy computation because these happens to be whole numbers. We have 8 minus 2 minus 2, right? For the first open parentheses, subtract 1/2 minus 1/2, got reduced, -1. Okay, so therefore we have 8 minus 4, which is 4, and then plus 1. That's going to be 5. Any question for this problem, folks?
No, it makes sense to
Yep.
me.
So the only thing different here is you see we're doing the same way of computing this iterated integral, right? Only thing different is now the limits is not all about constants. Okay, you have some variables inside. Okay, but the way is exactly the same for computation. How would these limits like affect the region, right? Later on, we're gonna see that. So first of all, I'm putting the solution here. So again, solution is 5. Okay, so in general, this is so-called iterative integrals. Okay, we're gonna talk about this next time again. You always start inside an integral and you go outside an integral. Okay. The outside limits of an integral must be constant. That's something we will see that later. Okay. For the outside, you must have a constant number. Otherwise, you don't get a constant towards the end. Okay.
So for that last problem, we would have to start with the the x.
Yes.
1 to x. Okay.
1 to x is for inside, right? You notice that it's for inside. Outside has to be numbers, constant numbers. Okay, we'll talk about this next time more. Okay. But in over this example 7, we're just going to show, even though it looks slightly different, but the way of computation is the same as all the constant limits. Okay.
Mm-hmm.
All right. We're gonna, yeah. So the last question almost here is, let's just revisit that example that we just did from 1 to 2 and 1 to x over dy dx. Let's see what kind of region that looks like. Okay, because we've already mentioned that this is not going to be a rectangle, not rectangular. So what does it look like? What we need to do is very simple. Let's see. I'm going to switch to pen. Okay. First of all, let's kind of recognize why would it be between 1 and x, right? So y is between 1 and x. X is between 1 and 2. Let's kind of look at this region, okay? This will be our main topic for next lecture, but here, let's introduce the idea. First of all, it's easy to see x is between 1 and 2. So 1 here, 2 there. So x must be between these two vertical lines, right?
Mm-hmm.
Y, it is between these two values. Okay, so y is greater than or equal to 1. So first of all, let's go to y equals 1. That's straight. That's just going to be a horizontal line, right?
Mm-hmm.
So horizontal line at 1. And secondly, you have y is less than equal to x. So we should look at y equals to x. Y equals to x is a straight line, right? Y equals x. That's a linear function, and then it goes through the origin because y-intercept is 0. So here is going to be, slope is 1. So this graph is going to be y equals x. Okay, with all of these lines here, let's see. X must be between 1 and 2, so it should be between these two strips. And y is higher than 1 and lower than x. So can you see the region being formed now? Folks, if you are supposed to highlight it, so we should be x is between 1 and 2, y is between 1 and x. So I should be highlighting this region right here. You can see that? So this will be my region R, which is not rectangular, right? So that's not rectangular region anymore, okay? However, even if it's not rectangular, the way of computing this double integral is the same as the way you compute a rectangular region, okay? We'll be talking about this more in next section, okay? Section 13 point, I always mess with my section number, 13.3. Okay, so here is the region as we have just showed. Okay. All right, folks, we're going to just stop at here today. Any questions? Is there any questions so far?
No question.
Yes. So like everything's fine? All right, then I'm going to assign the questions on my courses. I'm going to see you guys next Monday. All right. Have a good weekend.